Hello students, welcome back to another video of calculus. Today we will discuss some examples on divergence criteria. So the first example is show that limit x tends to 0, 1 upon x does not exist in R. Does not exist in R. So that limit x tends to 0, 1 upon x does not exist in R. We have seen the divergence criteria. So the first statement of the divergence criteria was, this was the first statement: if f of xn does not converge, suppose xn is sequence in domain which converges to C, but image of that sequence does not converge, then we will say that the limit does not exist. So here limit x tends to 0, f of x is equals to 1 upon x. So if we take domain as, let domain A is equals to R minus singleton 0. R minus 0 means whole real line except singleton 0. And if we take the here f of x is equals to 1 upon x. Now if we find one sequence in this domain which converges to some element in that domain, but the image of this sequence does not converge, that is, if we find one convergent sequence and whose image is not convergent in this in codomain, then we will say that this limit does not exist by first statement of divergence criteria. Now if we consider the sequence, xn is equals to, suppose xn is equals to 1 upon n for all n belongs to set of natural numbers, then clearly this xn converges, because if limit n tends to infinity, 1 upon infinity is 0, so this sequence xn converges to 0. So we have this xn converges to 0, but image of that xn, f of xn, that is f of x is 1 upon x, so f of xn means 1 upon xn, xn is equals to 1 upon n, so f of xn will be 1 upon xn, and 1 upon xn is equals to 1 upon n. So if we put 1 by n, and that will be n. Now limit n tends to infinity, f of xn is equals to infinity. So this f of xn, but f of xn is equals to this, does not converge, that is this f of xn diverges to infinity, hence given limit by first statement of divergence criteria, limit x tends to 0, 1 upon x does not exist. Now the second numerical is similar like this. Show that limit x tends to 0, 1 upon x square does not exist. Similar like this example, you can take the sequence xn is equals to 1 upon n and prove similarly that this sequence does not converge, that is this sequence diverges to infinity. This is for your homework. Now the next example is show that limit x tends to 0, sine of 1 by x, sine 1 by x does not exist. Sine 1 by x does not exist. Similarly, if we use the second divergence criteria, that is, if we find two subsequences of given sequence and that two subsequences converges to different limits, then we can say that this limit also does not exist. Now here we have given this function, suppose we will not out this function by g of x. So let g of x is equals to sine 1 by x, sine 1 by x, but we know that we have to find two subsequences. So we know that the sine of some t, that is, we know that the images of sine function are 0 and 1. 0 for n pi, sin n pi is 0 if t is equals to n pi, if t is equals to n pi for n belongs to set of integers, and 1 if t is equals to odd pi by 2, that is twice n plus 1 pi by 2, twice n plus 1 pi by 2. Now if we choose xn is equals to suppose n pi and suppose yn is equal to this twice n plus 1 pi by 2, then that will be two sequences. Also now let xn is equals to n pi, or xn is equal to suppose 1 upon n pi. Here we have given sin 1 upon xn, so 1 upon n pi will be n pi, and sin n pi is equals to 0. So let xn is equals to 1 upon n pi, where n belongs to set of natural numbers, and yn is equals to 1 upon twice n plus 1 pi by 2, twice n plus 1 pi by 2. Again n belongs to set of natural numbers. Then clearly this xn, that is this limit n tends to infinity, xn is equals to 1 upon infinity is 0. This xn converges to 0. Again if we put n tends to infinity, so 1 upon infinity into something means infinity, 1 upon infinity is again 0. Then this xn converges to 0 and yn is also converges to 0 as n tends to infinity, that is sorry, xn and yn two sequences which converges to 0. Now let the images of their sequence xn and yn. So g of x is equals to sin 1 by x. So g of xn will be sine of 1 upon xn, and sine of 1 upon xn means 1 upon xn is 1 upon n pi, 1 upon n pi. Just a second. Sine 1 upon xn means sine of 1 upon xn is 1 by n pi. So 1 upon n pi will be sine n pi, sine n pi, and sine n pi is 0 sorry, for all n belongs to set of natural numbers. So the g of xn will be 0 for all n belongs to set of natural numbers. Now similarly g of yn we will find also g of yn will be, g of yn means sine of 1 by yn. So sine of 1 by yn is 1 upon yn is 1 upon twice n plus 1 pi by 2. So 1 upon twice n plus 1 pi by 2 will be sine 2n plus 1 pi by 2, and sine of 2n plus 1 pi by 2 is 1. So this g of yn is 1 for all n belongs to set of natural numbers. So g of xn was 0 for all n belongs to, this is constant sequence. So this constant sequence converges to 0. This constant sequence sin n pi converges to 0. Also this g of yn is constant sequence which is equals to 1. So that sequence converges to 1. So this g of yn converges to 1 and this g of xn converges to 0 and g of xn converges to 0. So there are two sequences xn and yn which converges to same limit in domain, but their images, that is g of xn and g of yn, converges to different different limits in codomain. So the limit of given function does not exist by using the divergence criteria. Therefore, limit x tends to c, function was sin 1 by x, sin 1 by x does not exist. Limit x tends to c, sin 1 by x does not exist. Sorry. Now we will take the next example. Next example is signum function. So this is one note for you. The limit of signum function is also does not exist. So the signum function, first of all we will write the definition of signum function. Signum function is, the notation of signum of x is sgn of x, and this function is given by 1, 0 and minus 1. 1 for x strictly greater than 0, 0 for x is equals to 0, and minus 1 whenever x is less than 0. For negative numbers, signum of x is minus 1. For x is equals to 0, signum of x is 0, and for positive numbers, signum of x is equals to 1. So this signum function, and limit x tends to 0, this signum of x does not exist. Does not exist. For this function, if we take the sequence xn is equals to minus 1 raised to n upon n, then the image of this signum function does not converge. So this function is also does not converge. So these are some examples on divergence criteria. Now we will see some theorems on which are limit theorems. So next topic is limit theorems. So here we will see some statement of the theorems which are depend on limit. So in this topic, the first definition is neighborhood of C. So first definition. So let A be a subset of R and f from A to R be a function. F from A to R be a function, and small c be the cluster point of A. Small c, the cluster point of A. We say that the function f, we say that the function f is bounded. We say that the function f is bounded on neighborhood of C, that is the function is bounded on neighborhood of cluster point if there exists a constant sorry, if there exists a delta neighborhood, suppose n delta of C, n delta neighborhood of C, and a constant suppose m, which is positive number, m greater than 0, such that mod of f of x is less than or equals to m for all x belongs to A intersection that a delta neighborhood of C. Sorry, we know that the definition of bounded function, a function is said to be bounded if all the images of given domain, that is all f of x are less than or equals to m. But the function is said to be bounded on given neighborhood if for every element in that neighborhood f of x is less than or equals to m. Now we will see one theorem. The statement of the next theorem is so the statement is if A is subset of R and f from A to R be a function such that this function has limit f from A to R, as that is function is given by some, suppose you have given that function and that function has a limit, at x is equals to c, that c is a real number, x is equals to c and c belongs to R, then that f is bounded, that function is bounded on some neighborhood of C, So if A is subset of R, that is a domain of the function is subset of R, and f from that domain A to R, that function has limit at C, that is limit of the function exists at C, then that function is bounded on some neighborhood of that C. This is the theorem of this statement of this theorem. Now we will see another theorem, that is the algebra of limits. Algebra of limits, that is the addition of two functions. Algebra of limits, addition, multiplication by some constant, and division. So algebra of limits, let A be a subset of R and suppose f and g are functions on A to R, that is function from f from A to R, g also from A to R. If C be a cluster point of A, if C belongs to R be a cluster point of A, and limit x tends to C f of x, that is the limit of f is suppose L, and limit of g, that is limit x tends to C g of x is equals to suppose m, then the first statement is limit x tends to C f of x plus minus g of x, that is limit x tends to C f of x plus minus g of x is equals to limit x tends to C f of x plus or minus limit x tends to C g of x. By using the theorem on limit, you can write there limit is also addition of, that is L plus or minus m. Limit of f is L, limit of g is m, so addition or subtraction is again addition or subtraction of limits. Second is limit x tends to C f of x into g of x, which is equals to again L into m. Third statement is multiplication by constant, that is limit x tends to C, suppose k into f of x, where k is any constant, then k into f of x is k into L. Now the last one is limit x tends to C f of x upon g of x, limit x tends to C f of x upon g of x is equals to L upon m, where g of x is non-zero and m is also non-zero. This is the condition, m is non-zero sorry, g of x is also non-zero for all x belongs to A, for every A g of x is non-zero. These are some theorems. Now we will see limit at infinity in the next video.